Hi, today we're talking about net ionic equations, and a net ionic equation is going to allow us to strip a reaction down of all the things that aren't reacting and focus on the things that are reacting. So we have to understand that in a reaction mixture there are things that are there, they're present, they might even be part of a reactant, but they themselves are not actually undergoing any kind of reaction. They are not changing. Let's start with a synthesis reaction. And in a synthesis reaction, of course, we know that two things combine to make something new. Often two elements combine to form one compound. So in this one we have sodium and chlorine forming sodium chloride. And the sodium, if we follow it through the reaction, starts out as a neutral sodium atom and becomes a sodium ion, new stuff. The chlorine starts out as a neutral chlorine atom and becomes a chloride ion, 1- ion. So that becomes something new. Both have changed their electron arrangement. Both have started out as being neutral and finished as being an ion. Both have become something new. So both have undergone a reaction. Now, to take that same idea and the same steps that we went through and look at a single displacement reaction, now we have calcium chloride reacting with zinc. Sorry, not calcium chloride, copper 2 chloride reacting with zinc. If we look at the copper starts out in a compound, finishes up as a neutral atom. So it started out as an ion, a +2 ion, and it ends the reaction, it finishes the reaction in a neutral state. So it has changed from a +2 ion to a neutral. That's new substance. That has new properties and it's changed. The chlorine, on the other hand, starts out as being part of a compound and ends being part of a compound. It's not undergone any kind of change at all. Its job is to balance the charge. It's balancing the charge of the copper to start, it's balancing the charge of the zinc to end, but it itself did not change during the reaction. We call that being a spectator ion. Zinc, finally, starts out as a neutral atom and finishes as a neutral atom, and it finishes as a 2+ ion. So it has undergone a change. And again, as I mentioned, chlorine just shifts places from the copper ions over to the zinc ions as the copper ions decrease and the zinc ions form. If we were to take that reaction as we had it and turn it into what's called the net ionic equation, and that's just looking at the things that are undergoing changes, if we strip it down to all the ions combined and then crossing out the ones that are not changing, so the chlorine starts out as chlorine and finishes as, chloride I should say, and finishes as chloride. If we do that and we remove those spectator ions, then what we have is the net ionic equation. And the net ionic equation in this case looks like that. Copper ions react with zinc atoms to form zinc ions and copper atoms. Now the obvious question is, why would you bother? What good does that do? The simplest answer is it helps us to understand what's actually reacting. So in this particular reaction, copper 2 chloride reacting with zinc isn't the important part. It's the copper ions reacting with zinc. That's the important part. So we could change the reaction slightly, have different negative ions, but because those are spectator ions, they don't actually matter. The reaction is still between copper +2 ions, and zinc atoms. So as long as those things are present, the reaction will be essentially the same thing. Now, I have to have my net ionic equation to have three things in place. It has to be the net reaction, which means no unnecessary things. It has to be ionic. Now, in this case, there are some neutral atoms, but I have to show ions where there are ions. And finally, it's an equation. It has to be a balanced chemical equation. I'm going to give you some to try. And I would like you to pause the video at this point, take a few minutes, write these down, write your answers to them, and then we'll come back and we'll compare answers. Make sure you pause it and do this though. Okay, go. Okay, some of you didn't, but here are the answers. And just having the answers won't help you. You need to be able to do this on your own. But here are answers to the net ionic equations as I have them. So hopefully you're comparing your answers to my answers and where you're agreeing with each other. Okay, moving on. Double displacement reactions. And double displacement reactions are where we're going to spend most of our time writing net ionic equations. Double displacement reactions are a little bit harder to pick out what's going on simply because we don't have an element becoming a compound or a compound or one part of a compound becoming an element. We've got a compound and a compound reacting to form a compound and a compound. So it takes a little bit more skill. However, think about reactions where precipitates form. Oh, hey, look, that's one of my pieces of evidence that a reaction has happened. So it's the formation of a precipitate that is my clue to a chemical reaction. So what I want to do is I want to notice that in this one I have aqueous ions and I have things that are not aqueous. I have substances that are dissolved in water and I've got my precipitate, the solid, which is not dissolved. It would show up as low solubility on our table. So the reaction then is the thing that is producing the precipitate. So if I want to identify what's actually reacting, I need to figure out how that precipitate formed. And I don't mean in terms of at the molecular level. What do I need from the reactants to make that precipitate? Now, there's a piece of information that we sort of know, but we haven't really written down, we haven't formalized, we haven't really talked about. When an ionic compound is dissolved, so dissolved ions, dissolved ionic compound exists as ions. In other words, when I write down sodium chloride aqueous, what I have is not sodium chloride particles floating around. I have sodium ions and I have chloride ions, and they're floating around more or less independently of each other. And as I build my substance, or as I build my ionic compounds to go to, say, something like a calcium chloride now, it becomes calcium ions and 2 chloride ions. Notice what happens to the Cl2. We write the Cl2 because I need 2 chlorine 1 minus ions in there. But when they separate into individual ions, each chloride ion floats around independently of the other. If I make it even kind of bigger and uglier, so iron 3 sulfate, then what I have is the Fe2SO4 taken 3 times. It's not Fe2 particles floating around, but that means that I've got 2 iron ions. And I don't have clusters of sulfate, like 3 sulfates in a cluster. I have got 3 sulfates in the total compound, but when it's dissolved, they exist as individual ions. Lastly, if I have a substance that does not dissolve, then it does not exist as separate ions. Yes, it's still an ionic bond, but it now floats, sinks, because it's a precipitate, it's a solid. It exists as particles of, in this case, calcium hydroxide, not as separate ions. Okay, now if I go back to that ionic double displacement reaction that I had, if I take that thing and I break it down into its ions where appropriate, I end up with this reaction becomes, you ready? This, well, it's not a different reaction, but it becomes, this is how I would write it, and I need to get out of the way a little bit here. Now within that, and it's a big ugly mess, I understand that, but every substance that's said aqueous is broken down into its ions. The substance that was not aqueous, not dissolved, isn't. That's all there is to it. Then I start looking for spectator ions. And those are things that do not undergo any kind of change. So potassium ions are still potassium ions. The nitrate ions are still nitrate ions, not undergone any kind of change. But what has changed, what's gone from aqueous to not aqueous, is the iodide ions and the lead ions. Those things started out as aqueous, finished as a combined compound in a solid. So those are the things that are actually reacting. So getting rid of the spectator ions, potassium ions disappear, the nitrate ions disappear, and what I'm left with is the net ionic equation, which is this. 2 ions of iodide react with a lead plus 2 ion to make lead 2 iodide as a precipitate. Now let's look at one more that's a little bit bigger, a little bit uglier, got a little bit more stuff. And what we'll also try and do is we'll shortcut it a little bit. Now I know I always warn you not to take shortcuts until you're ready, so we hope to be ready. But we also want to make sure that we understand what's going on with all the ions and things like that. So we look through the reaction to find out what's actually not reacting. So anything that's labeled part of an aqueous on the reactant side and is still part of an aqueous on the product side is going to be a spectator ion. Now of course, because it's double displacement, who they're paired up with, or what they're paired up with I should say, changes, but the fact of the matter is sodium starts out as aqueous, it finishes as aqueous. Chloride starts and finishes as aqueous. So those are spectator ions. The things that are actually changing, the things that are changing their configuration, their state, going from an aqueous to a solid, is the carbonate and the aluminum. So I look through the reaction and I basically get rid of the spectators. But now it's not just CO3, I have to remember that that's an ion. So I have to include the ionic charges for these things. Remember, it's a net ionic equation. I also have to remember that the balancing numbers that are there are also part of it. So when I look at the reaction and start shortcutting things, I need to make sure that it's net, so no spectator ions. It's ionic, so I've figured out or included the ionic charges. And it's a balanced chemical equation. So for this one, the net ionic equation becomes that. So remember, I found the spectator ions and kind of canceled those out. I figured out the ionic charges, or I looked them up, the ionic charges for the things that were remaining, and included the balancing numbers as well. I'm going to leave you with a couple to try, but we're going to be, which looks like less than what you had for the single displacement, but we're going to be doing more with this in class. So our opportunities to practice with double displacement reactions will actually be much larger than our opportunity to practice with single displacement reactions. So after that, we'll talk in class, we'll try them out, we'll make sure we know what's going on, we'll quiz you on it, it'll be on the test, it'll be spectacular. Talk to you later.